In this video, we're going to combine the energy balance with species conservation equation in a mixed flow reactor, and we will see the nonlinearities associated with temperature effects in a adiabatic mixed flow reactor. Energy balance in a mixed flow reactor under adiabatic conditions. The species conservation equation for a mixed flow reactor was derived as tau is equal to Ca0 minus Ca divided by R sub A, with a minus in front. And for a first order reaction, if R sub A is equal to K times Ca, or is equal to K0 e to the minus E over R T times Ca, we were able to derive the relationship between the Damke-Euler number tau k and conversion Ca0 minus Ca0 1 minus x divided by Ca0 1 minus x, where Ca0's cancelled, and conversion was tau k divided by 1 plus tau k. Now, if tau and k are constants, this relationship gives rise to a well-behaved increase. All right, for small tau, x and tau relationship is almost linear. For very small tau, x and tau relationship is almost linear. For very large tau, or for very large tau k, x and tau relationship is in the asymptote that x is unity. Now we are going to look at how k is influenced with energetic interactions under adiabatic conditions, how we are going to solve the energy balance to relate the temperature to conversion. For this, we are going to write down the energy balance for an open system at steady state. We're going to have the du over dt term to be equal to 0. We're going to have the net rate that energy flows in with the flowing streams, the net rate, the energy flows out with the flowing streams, plus heat, plus shaft work, minus P dV over dt. We are going to solve this problem for an incompressible fluid. is the shaft work. So let us focus our attention to these terms. Fi is equal to Fa0 times theta I plus nu I over nu A times x. Theta I is Fi0, Fi in over Fa. Let us use in here instead of 0. So when we bring this stoichiometric relationship into our equation, let us see where it is going to lead us. I'm going to focus my attention only to those two terms. So I have Fi in, Hi in with a summation sign minus another summation sign Fa0 Fa in times theta I plus nu I over nu A times x times h out. This is the term that we're going to rearrange. So we can write Fi in as Fa0 times theta in and we will rearrange. So starting from the most general form of the first law of thermodynamics, we have introduced the molar flux of species I in terms of their stoichiometric ratio relative to component A and their corresponding reaction stoichiometric coefficients nu I over nu A and conversions. We have observed that the nu I over nu A times H out terms are related to the reaction enthalpy change through the expression minus delta H reaction, and the overall energy balance has now taken the form under steady state conditions. 0 is equal to Fa in times Cp mean times the temperature difference between inlet and outlet plus Fa in times conversion minus delta H of reaction plus heat exchange plus the shaft work. For the heat exchange, we might have a heat exchanger with an overall heat transfer coefficient times delta T log mean and of course the heat exchange contact area A. For the shaft work, we have to know the energy introduced through the impeller. This is going to be one of our heat removal terms. The other heat removal term is going to be the stream that is leaving with its energy out of the reactor. For an adiabatic reactor, this heat term is going to be 0 under the conditions that shaft work is negligible. Our expression simplifies to a relationship between the outlet temperature and the rest of the reaction parameters. X times minus delta H reaction divided by the average heat capacity. When heat and shaft work terms are cancelled, FA in terms cancel one another, and the temperatures transferred to the left side of the equation change sign. Of course, this is going to have an inlet temperature as well. So for an exothermic reaction, enthalpy change of the reaction is negative. With the minus sign here, with the negative enthalpy change of the reaction, we are going to have a positive term that changes with conversion. And outlet temperature will always be greater than the inlet temperature under adiabatic conditions. And for endothermic reaction, enthalpy change of the reaction is going to be greater than 0. And outlet temperature will always be less than the inlet temperature, unless any other energetic interaction is present. Now, given this, if we plot space-time versus conversion curve, space-time versus conversion curve for a first-order reaction, our relationship was if you transfer from the other side of the panel tau k over 1 plus tau k, and k is a function of temperature. K is a function of temperature, and the relationship of temperature between temperature and conversion is given by this equation. For the isothermal reaction, our relationship went like a plane sigmoid, where temperature was constant, that curve shifts towards right for an endothermic reaction, in other words, we need larger space-times to achieve the same conversion, because as the reaction proceeds, temperature decreases and reaction slows down. For an exothermic reaction, the curve shifts to the left, as indicated by dot dash lines. This is for an exothermic reaction. And under the conditions that reaction enthalpy is so large that the system undergoes instabilities, our curve may show instabilities as shown in the final curve, that our reaction ignites rapidly or when we are cooling it down, the reaction may extinct. Very rapidly. This portion of the curve is stable. This portion of the curve is stable. However, this portion is unstable. As you can deduce, as we increase the space-time, the conversion decreases. And this part of the discussion is the reactor stability discussion. We will consider this in depth in a subsequent video.